Hi, everybody. My name is Riley, and I'm here to talk to you today about why I believe reliable serverless needs distributed transactions. Specifically, I want to talk about how the rise in serverless computation and cloud computation has caused a shift away from systems that are strongly consistent to those that are eventually consistent. Furthermore, I believe that this change makes application developers' lives more difficult and their applications more likely to be incorrect. And a general theme of this talk is anytime you make application developers' lives more difficult, you increase the likelihood of bugs, which decreases the reliability of the overall system. So I think because of some new tools that are in the space, now is a fantastic time to reintroduce transactional primitives on top of serverless computation. But first, how did we get here? Over the past 15 or so years, I think we've seen a trend from monoliths to microservices and serverless functions, brought on by a desire for looser coupling and better scaling. But an unintended consequence of this is that we have introduced more eventual consistency into our applications. And I'm sure this is obvious to most people, but the reason why this has introduced more eventual consistency is when you're working within a monolithic framework, if you want to update multiple pieces of state, you just open a transaction to your database and you're done. In microservices world, these different microservices are often backed by completely different databases, or if they're not, they're definitely being opened from different processes that probably need some level of coordination to actually manage a transaction. Because it is difficult and error prone to add transactionality on top of microservices, it just typically isn't done, or we will opt for something less than strong consistency. So why this trend in the first place? Why did we move from monoliths to microservices? I'm sure this is ancient history for some of you, but this modularity makes it, microservices are great. Like they have a lot going for them. Their modularity makes it easier to understand, modify, and test your code. It gives teams engineering agility because you're not beholden to some kind of bloat release schedule. For anyone who's ever been a part of that, what a headache it is to try to get your teams in. Tests were passing, then Reboot is just your team and makes it much easier to release software. We can have technological diversity within the organization because each team is free to choose their programming language, database, framework. And all of this is encapsulated behind a well-defined API. And perhaps most importantly, it makes it easier to scale the application and to scale the company. So microservices, I think when we reflect on these changes, we can safely say that these changes were built for us. Container orchestrators were built for operators, not application developers. Application developers were told to split their applications into microservices because it made it easier for us, the operators, to run their applications on container orchestrators so that we could do software and hardware maintenance, provision, and provision resources, et cetera, et cetera. So let's take a look at a concrete example of how this can make application developers' lives more difficult. So this is just a real bog standard checkout function. You've got a cart service, a shipping service, a payment service, e-commerce service. We get the items out of our cart. We prepare a shipping order, which I guess is calculating shipping. We authorize the user's charge. We ship them the orders, and then we empty the cart. And we send them an email that they have received their items, but they can get their items to process too. So I actually think this looks great. It's used very logically. We have a series of steps here. They look like function calls. We're doing things compositionally. Composition and modularity is what allows us to reason about and scale our applications. And from an organizational standpoint, perhaps most importantly, independent teams can now all be different services. We can have a cart team. We can have a shipping team. So this is all awesome, but there's a bug. Does anybody see what it is?
One of the items in one of the application never responds, or one of the thing never goes through.
Yes, absolutely. What if the computer running this checkout function dies? Right here. That's actually not that hard to imagine. These are now potentially asynchronous network requests that take some time. So it's totally possible that our computer dies here. It's also, if we're running this at scale, it is likely that our computer dies here at some point as we're running these checkouts. Now, if I'm the front-end client and I get an error from calling into the checkout service, I'm just going to want to naively read it. That's what I want to do. And I'm just going to assume that it's hopefully a intermittent network failure. I just want to do it again. Is it safe to run this again? A computer previously failed at this point. I would argue that it's safe. From the end user's perspective, we haven't charged their card, we haven't shipped them an order, and we haven't emptied their card. So their world is consistent. Internally, we might have introduced some inconsistency. Shipping, prepare, ship order is a mutating function that updates state. There's a chance that we have done that twice. Of course, card get items is a reader function, so you can run that as many times as you want. Well, if I'm the shipping team, it's probably well within my purview to dedupe requests. So this actually isn't so bad. And that's why this issue is so pernicious, because sometimes, often, it's not that big a deal. But sometimes it is. What happens if we happen to die, right? Now, if we naively rerun again, and we succeed the second time, we will have charged the user's card twice and only shipped them the item once. This happens so regularly that there's all sorts of stuff built into payment processors to handle this exact issue. But it's not built in everywhere. And I would argue that you have absolutely seen this bug yourself at some point in your life. This is a real screenshot from the CEO of my company tried to deposit a check. The check, he took a picture of the front and the back. The check deposit failed, and his options were, okay, I guess I don't want to deposit my check after all. Or try again. Of course, he clicked try again. And then multiple hours later, he got a call, or I'm sorry, he got an email from Schwab telling them to call him. And when he did, they very politely accused him of bank fraud. If you think about like just using software in your day-to-day life, my guess is you've absolutely seen this. I see this all the time on Venmo. I click send, and nothing happens, and I click send again. It's like, whoa, slow down. Might be moving too fast. Yeah, this problem is everywhere. So at this point, you're probably in one of two camps. Either you're thinking, yeah, duh, this is not the way we code microservices. Anyone who has used microservices in anger does not write them this way. Or you are in the other camp where you're thinking, oh no, I think it's possible that I have these bugs in production myself. And if you are in that latter camp, you would very much be forgiven. This is Google's microservices demo example. It's a very popular example. If you type, I think, microservices into GitHub search, this is the first or second. You type in demo into GitHub search. I think this comes up on the first page. This example has this bug in their checkout. It's written in Go, so it looks a little different, but it 100% has this bug. If you use this example in production, you will have an inconsistent system. And just as like an aside, it's a pretty big API smell, I think, when the most obvious and simple way of using a tool leads to an incorrect result. And I think especially in the age of AI, we want our corpus of code to be correct because this is what we're feeding to the AI. Or maybe this isn't what we want. I don't know. Maybe we want to all still be employed. Maybe we want a bunch of buggy distributed system software that we can then go fix. But I think it really behooves us to not release examples that actually result in inconsistent distributed systems, which this one does. So as operators, it was our responsibility to figure out how to move from an inconsistent to a consistent world in a distributed systems environment. There are ways to do this. One of them is event sourcing. The other one is durable execution. Event sourcing has been around for a while. Durable execution is the hot new kid on the block. For those who aren't familiar with event sourcing, you're basically storing all state changes as a sequence of immutable events in something like an append-only log. And then durable execution functions and workflows are persisted as they are run in memory, and then they're retried on failure and run to completion. So let's take a look at the slightly more deployed and older example. So this is a really common way to fix the inconsistencies that arise in distributed systems. Basically, the way that this works is, so we write everything to a queue. And the great thing about that is if we fail at any point, we can just replay all of the changes that happened up until that failure. If they're cached, we just return the result and then we continue on. So this is great. This brings us from an inconsistent world to a consistent world. What cost? We now have to operate and stand up something like a distributed queue. Okay, not so bad. It's pretty great. But what has this done to the application development? We have swapped out the common request response pattern in favor of PubSub. Instead of calling a function, we publish an event. Instead of returning a value, there's either a callback or a subscriber response view. So this version of control completely upends the application developer's mindset. It can lead to callback hell. It makes it much more difficult to trace the path of the code, the kind of following functions and seeing what they do. That's inverted. And now we have this kind of central glue layer in our company we call this queue-glued software. And what that means in practice is that a lot of business processes just end up in this queue, and we've lost a lot of the benefit of the separations of concerns that we got with microservices in the first place. There are other strategies around doing this kind of thing, Saga-style transactions, like I mentioned, durable execution, which honestly, I think probably is getting such popularity now because event sourcing is just such a headache for application developers to use. They want something that's a little simpler. But all of this, though now consistent, is still only eventually consistent. And so what this means is now if a dev gets a failure, there is a very good chance that they're going to need to write compensating actions to roll back the failure because we've updated the state of the world. So we need to, oops, sorry, we didn't want to do that. If we get a failure here at we've done all this work before, now we need to roll it back. And this is just more code that developers need to write. It's more code that they need to test. And if I'm a front-end client, I don't want to I don't want to think about, I hope that team implemented their rollback function correctly. I just want to be able to naively retry without having to think about all of that. Oh, by the way, everything that I'm saying here about microservices applies to functions and lambdas as well. Those are like microservices. In many ways, they can exacerbate the problems of microservices. Okay, so what is incredibly ironic about all of this is that concomitant with the rise in queue-glued software, substantial progress has been made in the area of strongly consistent distributed databases. So we've got Cockroach DB, we've got Youngbyte. Of course, we have Google Spanner, which has been around for a long time. So if we have these strongly consistent distributed tools at our disposal, why all of this eventual consistency in our applications? It's pretty obvious. It's because the inconsistency arises at the application layer. So it doesn't matter if you have a Spanner as your data store. If you stick a Kafka in front of it, it is now eventually consistent. Yeah, basically what we've had is two kind of trajectories. And unfortunately, they're not meeting into strong consistency. We now have a lot of work done to make things consistent, but eventually so. In the application layer, we've done a lot of work to make things consistent and strongly in the database layer, and the two are not meeting. At this point, you might be thinking, especially if you're greenfield, you're probably thinking, to hell with all this. I don't need any of this. I don't need event sourcing. I don't need microservices. I don't need durable execution. I don't have any scaling requirements. So Why don't I just use a Rails and a Postgres and figure all this out later? And that is exactly what we, the software community, have been telling people to do. People whom I respect very much, who are much smarter than me, people like Martin Fowler, say you shouldn't start a new project with microservices, even if you're sure that your application will be big enough to make it worthwhile. The conventional wisdom is to only adopt microservices when you graduate off of your monolith. But in practice, typically what that means is that the scaling requirements of your business make it such that you need to adopt microservices. And if you've ever tried to keep something alive that is inherently not scalable, while also completely rewriting it into a different system, that's not a great place to be. That's a bad time. That's how they did it at Twitter, but it's not because they wanted to, it's because they had to. I think all of this is evidence that we gave you the wrong abstraction. Like microservices and lambdas are the wrong abstraction. Namely, they force the application developer to think about something that has absolutely no pertinence to solving their business problems, specifically how this code is deployed. So microservices conflate logical boundaries, how code is written, with physical boundaries, how code is deployed. So what we really want is a system where application developers can write their code logically as monoliths, but then under the hood, a runtime decides how to distribute and run their applications across resources. That would be the best of both worlds. From the operator's perspective, we now have something that it feels a lot like microservices with all their benefits. From the application developer, we have something that feels like Rails. So, going back to this earlier example, the problem with this was that the developer's intent was that this gets executed autonomously and idempotently if retried. So let's try to make a system like that. Let's say this is just like an execution context of this thing on the right. I've only shown a couple of these because the rest of them are the same. But basically, let's imagine now that we have just added one little line up here, which is a context. And it's a transaction context. And the contract of a transaction context is that everything in here succeeds or everything fails. So how do we actually achieve that in practice? What we would do is when we start this checkout function, we call this method that reads data right here. We call out to that service and we log it. And then when we call this mutation right here, we persist that we made the call, but we do not commit the results. It is not observable to the outside world. And then here, same thing. And it isn't until this entire function returns that all of the results are committed and the cart is unlocked. Sorry, I just missed my show notes. At this point, I can hear what you're thinking. Oh boy, isn't this expensive? We're locking a service so that we can do a read. And you're right, it is a little more expensive than something like a Saga style transaction. But if you are, the way to architect a system like this is to keep cart really small. Don't think of it like a cart service or a cards table. Think of each one of these cards as an individual row in a database. And taking a read lock on a database while a transaction is happening happens all the time. Shouldn't be too scary. So going back to the performance, it is true that using transactions in this way is slightly less computationally efficient, but I believe this is a worthwhile trade-off. Taking from the Spanner paper, we believe it is better to have application programmers deal with performance problems due to overuse of transactions as bottlenecks, rather than always coding around the lack of transactions. It's much easier to scale computers than it is to scale people. And if you are making your application developers' lives significantly more difficult as they program their applications, that's not a worthwhile trade-off, even if you get some machine sympathy for it. The other benefits of this is that once you start thinking transactionally, just a lot of really nice things just fall out of your programming. We see here that the only data dependency between these calls is cart get items. We've got a distributed system. Let's just do all this stuff in parallel. There's no reason that we need to wait for each one of these calls. Furthermore, We can change the implementation so that empty cart returns your items. We can get rid of cart get items entirely in this checkout process. And there's no risk that you're going to empty your cart's items before processing the rest of the order because of the guarantees of a transactional context. You're welcome to build a system like this yourself. There are others off the shelf. The one that I love is the one that I've been working on for the past 2 years. It's called Reboot. So in addition to introducing these transactional primitives, we also have asynchronous workflows for things that don't require a transaction or actually would be detrimental if they were a transaction. Things like loops that run forever. That's a great use for asynchronous workflows. And then near and dear to my heart is we also have a React integration. We code generate for you React custom hooks that reactively update anytime your backend state changes. And this reactivity is transitive throughout the entire system. So you have a materialized view that, is based on a bunch of different other data. If any little piece of data anywhere in this DAG changes, all of these things re-execute, and that benefit is pushed all the way to the insight here is that you want things to be consistent from the end user's perspective. That's the thing that really matters. And if your item potency, transactionality, consistency ends at the back end and does not extend to the front end, then your end users actually aren't getting the benefits of this strongly consistent transactional system. So that's Reboot. Yeah, this example is actually what our code looks like. So you have this transaction context and the guarantee is everything in here runs or not. And I think this is the best of both worlds. So if you're interested in building the next generation of cloud native abstractions, come talk to me. Check us out. Thank you.